Hi, my name is Russell Schuler, and this is me doing the extra credit assignment. So first, this question is written out here, and it's asking you to find the magnitude of the acceleration of the boxes and then calculate the magnitude of tension in the string. So first, to find the magnitude of acceleration in the boxes, we first have to do free body diagrams for both of these boxes. So for box A, we have the components in the y direction and in the x direction, and then same over here. And on David's problem, he forgot to do the x component of the force of A. So right here should be force of A sine theta of A pointing to the right. So this messed up the entire problem basically and caused the answers to be incorrect. So I'm going to show you how to do it the right way. So first you do, if we're working with box A first, you want to find the net force of A in the y direction. So we have the top minus the bottom. So we have FNA plus FA cosine of theta A minus MAG cosine of theta A equals 0, because there's no acceleration in that direction. So then if we solve for FNA, we move these to the other side. So MAG cosine of theta A minus FA cosine of theta A. So, and to make it easier, we can just factor out the cosine of theta A. So FNA equals cosine of theta A times MAG minus FA. Okay, so now if we want to find, still working with A, we're finding the net force of A in the x direction, so this way. So since we're accelerating upwards that way, we're going to do right minus left, so acceleration can be positive. So we're doing this minus this. So FA sine of theta A plus T minus FKA, and that's the friction kinetic. Since it's moving upwards, the friction is going to be opposing it the other way. So then it's minus MAG sine of theta A, and then this all equals MA times the acceleration. So then if we want to solve for T, so we're going to move everything to the other side. So T equals MA times acceleration minus FA sine of theta A plus FK of A plus MAG sine of theta A. And then now we're gonna, we know the friction is equal to the coefficient of kinetic friction times the normal force. So we have the normal force up here, so we're gonna multiply those two together and substitute that in for here. So it's just MA times acceleration minus FA sine of theta A plus the coefficient of kinetic friction times this, so cosine of theta A times MAG minus FA plus MAG sine of theta A. Okay, so now if we're looking at B, we're going to look at the net force of B in the y direction. So now we're looking this way. So we're going to do this minus this. So Fn of B minus MBG cosine of theta B equals 0, because no acceleration. So then we know those just equal each other. F and B equals MBG cosine of theta B. So now, if we look at the net force of B in the x direction, so going this way, and acceleration is going down this way, so we're going to do this right minus left. So it's FB plus MBG sine of theta B minus T minus FKB equals MB times the acceleration, because now we're looking at Newton's second law. So now we can use this tension that we got here, plug it into this tension of this new equation. And since it's minus T, we're just going to switch all of the signs here. And looking back at David's problem, here he did not make this a minus from here when it should have been, since we're supposed to distribute the negative throughout. And also before, he didn't have something I forgot to mention. He didn't put the cosine of theta A in this from right here. So this should have been FA times cosine of theta A, which he had written, he just forgot to write it. So to keep going, now we're gonna move over here in a minute. So FB plus MBG sine of theta B minus, now we're gonna minus all of this. So minus MA times acceleration plus FA sine of theta A minus UK cosine of theta A times MAG minus FA minus MAG sine of theta A minus kinetic friction of B equals MB times acceleration. So now we're going to move this MA times acceleration, we're going to move it over to the other side, and then we're also going to substitute in this friction, which is going to be mu K times the normal force of B, which is here. So we know that. So it's going to be FB plus MBG sine of theta B plus FA sine of theta A minus mu K cosine of theta A times MAG minus FA minus MAG sine of theta A minus, and here's the substitution, mu K times this, which is MBG cosine of theta B equals MBA, and then here's where we add this to the other side, plus MA times acceleration. So now we're gonna factor out in the A in these, so we're just gonna rewrite this real quick. So all of this sine of theta B plus FA sine of theta A minus mu K cosine of theta A times MAG minus FA minus MAG sine of theta A minus mu K MBG cosine of theta B. Okay, so all of that equals, we can pull out an A, and it's going to be MA plus MB. And now, finally, for acceleration, we're just going to do all of this divided by MA plus MB. So if we just rewrite it out to show, it's going to be all of this So all of this divided by ma plus mb. So acceleration. So we have all the information up here that was given in the problem. So just plugging this all into your calculator, you'll get 1.433 meters per second squared. So that is the acceleration. And in David's problem, just one small mistake. He just forgot to put the squared for the units, which you should have for acceleration. So now for the second part of the question, calculate the magnitude of tension in the string. If we just want to solve for tension, we already have this equation up here. So we're going to use that and plug in the acceleration we just got. So ma times a minus fa sine theta a plus mu k cosine of theta a times mag minus fa plus mag sine of theta a. So that's just bringing this tension down here. So after plugging all of that in your calculator, using all the numbers that we have, we get the tension as 238.935 newtons. So that's the answer. And just because I think I forgot to explain before, just how we got some of these, we have the normal force pointing up and we have the mg pointing down, but we need to separate it into the components. And using the rules of theta, we can know that this is the mg cosine theta, this is the sine going this way, and we have friction. And then the components of A, same kind of deal. So cosine going up, sine going to the right, and the tension of the string. And same over here, but tension of the string is the other way, and there's friction moving the other way because it's moving down. And then we have the force, and we have the gravity, the force of gravity components as cosine and sine this way, and then the normal force, of course. So that's it. Thank you.